We're happy to have with us today Eliad Tsfadia from Bar-Ilan University. Started in Tel Aviv, then spent some time in Georgetown, where soon he did his work with Kobe and Chow. And he will tell us a little bit about differential privacy, as we saw, and specifically about optimizing things in the differential privacy way, which is something that seems like more and more people are trying to do these days. So every step there is quite helpful. So, thank you.
Thank you. So, hi everyone. Eliad, I'm very happy to be here. And I'm also very happy to hear an intro to my paper. Yeah, very nice. So, but we will start from the beginning, from the definitions, and if you didn't understand previously, then that's okay. We will do that again slowly. Okay, so this is about something called quasi-concave optimization, and as we will see more importantly, why this is important to other applications, to other geometric problems, like half-spaces and things like that, okay, in high-dimensional settings. Okay, so what is differential privacy? Okay, so we are thinking about, we have an algorithm, okay, that gets a data set as input, a data set of elements, where we think about the elements as individuals, and the goal is to compute something about the data set. We can think about any type of algorithm. It could be a simple algorithm that maybe do some average, or it could be even a learner algorithm, okay, that gets a training example out of the model. But basically, we think that this is the model, the algorithm does something. And regardless of what the algorithm does, we want that the algorithm will have the property that one record does not change the output distribution of the algorithm too much. What do I mean by that? So if we think about a different execution, for example, let's say that we change one of this, we change x2 to some x2 prime, and we look now at the output of the same algorithm on this s prime with this one change. We want that somehow those outputs will be almost the same, okay? And why this gives us some kind of a privacy? So we can think of, let's say that, let's think that this data set, let's say, are images, and this is Alice images, Alice image in the x2, and in the other data set, maybe we use a different image or some fake info. So we somehow, if the outputs look almost the same, we basically guarantee that. So if you are like afraid that maybe the image will appear in the model, somewhere you can reconstruct the image from this execution, I can tell you that it's not going to happen, because even if the image doesn't appear in the training set, still the output will look almost the same. So if the image doesn't appear here, won't appear here. Okay, so as long as the output doesn't really depend on the single record, this is basically gives us a very strong privacy guarantee. Okay? So hopefully we can have like those distributions to be exactly the same. Okay? Maybe why we need to be like almost the same. So it turns out that you cannot do it. Like in order to compute something meaningful with respect to anything that really is dependent on the data set, some statistic about the data set, you must have some privacy loss. Okay? If those distributions are equal for any neighboring data sets, it basically means that the algorithm just ignores the data set. Okay? So there must be some kind of a loss, and usually this loss is measured by epsilon delta parameters. And formally the definition says that A is epsilon delta dp, differentially private, if for any neighboring data sets, S and S prime, neighboring I mean they differ in one record, and any event H, subset of the output domain, we wanted the probability that H occurs in AS is epsilon delta close to the probability occurring in AS prime. Okay? Usually, just to give some concrete parameters, we think about epsilon as a small constant. Y is small constant, so once epsilon is a small constant smaller than 1, we can think about e to the epsilon like 1 plus epsilon, somewhat the same. And this basically, without the delta parameter, it's like any event here occurs with almost the same probability in a neighborhood execution. But usually we also add some delta, which this delta is like 1 over some, let's say some large polynomial in the number of elements. This delta, if we can think about it as maybe a probability that some bad thing will happen. Maybe with some very small probability we're going to, I don't know, output the data set. But as long as it doesn't happen, it's really like very private. Yeah.
Just to clarify, when you say neighboring that's S and S tag, you mean that the only difference is one record?
Yes. Yes, exactly.
And there's no other definition with like multiple records that are different with that.
The neighboring is different by one way. Yeah. There is some one record that they have.
Thanks.
Any question about the definition? Okay. Good. So now the question: what can we do? So we have like a definition of what is like what we want to achieve, like what gives us privacy. And the question is, what can we do with this definition? And what we are going to focus now is on some kind of an optimization problem. So the title was about quasi-concave functions. So I'm going to describe what are quasi-concave functions, and after that I will show you like very basic tasks that we can do with that, and after that even more complex. So what is quasi-concave functions? So we know what is a concave function, right? Concave functions, it's above the line between 2 points, and quasi-concave is something that's not exactly concave, but it still has the property that if you look at 3 points on the function, then in the middle it always be at least the minimum. Okay? And okay, so this is a quasi-concave. Also, as shown in the intro before my talk, we also talked about we are still in the quasi-concave example. So let's just give a concrete example. So let's think about the data set as just points on the line. So we have the data set of a bunch of points on the line, and now we define like the depth or the Tukey depth of a point as like how depth the point is, like what is the minimum number of points from the left and to the right. Okay, so for example, this point has Tukey depth 4 because it has 4 points here and 4 points here, as the minimum is 4, and this point here has Tukey depth 3 because it has 3 to the right. Okay? So here this example of function, and this function is also a quasi-concave. Because as you can see, it doesn't matter, you will take any data set that you will take of points, and any 3 points that you will choose, the f of b will always be at least the minimum of fa and fc. Okay? You can easily prove that. It's not hard to claim.
Is there an intuition for this? That's called depth. What is deep about?
The depth you can think about like it's basically a different analog of the definition. Is how many points you need to remove in order to make the point outside of the outside of the segment. In the high definition, you can take this how many points you need to remove in order to make it outside the convex hull of the other points. Okay, it's basically how deep it's inside the set of points. Okay, so I'm just defining it for one dimension, and as we will see next, we're going to extend it to a high dimensional setting. Okay, but basically it's the same spirit of the definition. Okay, so this is the two-key depth functions, and in one dimension. Right now we are only talking about one dimension. And I also need to define several low sensitivity. So a function f is sensitivity k. Now it's a function of the data set. So if we take a data set and a neighboring data set that only changed by one record, the value would be at most, the difference will be at most k. And again, if we look at the two-key depth function, it has sensitivity 1. If we look at the function now as a function of the data set, not as a function of the point, okay? And for example, let's say that we're in this picture, and now let's say that we are moving this point here, the green one, from here to here. Then what's happening is that this A decreases by 1, this B decreases by 1, increases by 1, this remains the same. But eventually you can show that it doesn't matter. If you change one point, the two-key depth of any point on the line will change by at most 1. Okay? Okay. So we have those two definitions, and now what's the goal? What we're trying to say? So we saw the privacy definition, we saw like two properties of the function, and now we're going to decide what is like the quasi-concave optimization that we are trying to achieve here. So our goal is to construct an algorithm that gets a data set S and some function Q, which has those two properties, that it's quasi-concave and has sensitivity 1. For example, the two-key depth function. And our goal is to output some Y that basically satisfies two properties. First, we want this Y to be almost close to the maximum. We want, with high probability, that the value on this Y will be close to the maximum of the function. Okay? For example, in the two-key depth, we want to find a point which is very close to the median. Okay, with really high depth. Yeah.
Can you explain again what is the two-key depth function? If you use it to various examples.
Yeah. So again, the two-key depth. Well, let's go back. So the two-key depth function is the data sets of points on the line. When you give me an A, for example, Y is like could be A, B, or C. So it's when you give me some point on the line, you look how many points on the left, how many points on the right, you take the minimum. Okay? Or equivalently, how many points do you need to remove in order to make the point outside of, like, if I remove those 4 points, then these points remain outside of the segment of the other points. Okay? Okay. So the goal is to construct such an algorithm that on the one hand, we want to maximize the function. So without privacy, and let's say, so in this talk, we're not going to focus even on running time. Okay, let's say that what we are going to show here is even like information theoretic. What simply we can do. Like without privacy, it's not a problem. Just, if you don't have a running time restrictions, just compute the maximum. Okay. But the problem is that I want also that this algorithm will be private. So on the one hand, I want to compute the maximum of something close to the maximum of the function. But on the other hand, again, I want to satisfy differential privacy. So if I change one record, and I want those output to be almost the same. Like, the distribution of this Y and Y prime should be almost the same. Okay? So now the question is, even without running time restriction and just information theoretic, what should be the size of the data set in order to satisfy this two constraints. Okay?
Do you assume that entered in the data set of IID or something?
No, right now I don't assume that. No.
I mean, do we always have a case that everything in the data set is zero except one entry which is content? If we remove that one, the maximum will change.
It depends on what is the function, okay? Like, if we look at the cookie function, so even if one point is very high,
Yeah.
okay, so it's really dependent on what is the function, right? If you look into a function that this point, which is very far from the other, it has a very high sensitivity, then it will be hard. But I assume right now that this function has a nice property that it has sensitivity 1. So basically, if you take any neighboring data sets, then the value will be post 1, changed by post 1. Otherwise, if you think about the function where it's not the case, it will be harder or even impossible to do something unique. Okay? Okay. So let's focus now on a simpler, easier problem. So let's say that we don't, like this problem that we described here is like we somehow aim for any function that satisfies those two properties. Okay? So we can say, okay, well, I talked about the Tukey-def, and let's just say, okay, just focus on the Tukey-def function and give me, like, data set are now a set of points on the line, and just give me a point with high Tukey-def, which basically estimating the median. Okay? We have points on the line, we want to estimate something that is close to the median of the points. For example, let's say that the median is here, the maximum is here. Output something close to it will be acceptable. Okay? And we can think about even an easier problem. The easier problem, so just to mention that the Tukey-def is, the maximum is always n over 2. So you can just replace the maximum with n over 2. And an even easier problem will be the interior point problem. Just output something with Tukey-def, positive Tukey-def, okay? Even this one will be okay, this y here. So basically, it's like a very, very trivial problem. I give you a bunch of points on the line, just give me something between the minimum and the maximum of the points. Which is like a very, without privacy, it's nothing, okay? There is no question like how to do, even output each of the points would be a good solution. But the problem is how we do it with this privacy restriction. Okay? Okay. So let's think about this really simple problem. Again, the interior point, we have a bunch of points, we want to output something between the minimum and the maximum. So if we have only one point, we can solve it, okay? Because this one, if we have utility, the solution must be here, and if we change this one point, basically we cannot achieve both utility and privacy. It's very clear that one point is impossible. What about 2 points? So again, it basically also a problem. So maybe this is the 2 points are here. So if you have an algorithm that output interior point must output something in this segment, but if I remove this point here, then the algorithm must output something in this segment, so it cannot be both private and accurate. Okay? Again, accuracy means that you must output something in between the minimum and the maximum. So if you have an algorithm that satisfies that, you can show it cannot be private. Okay? Because those segments are almost disjoint. So we can continue to larger ends, but in fact, this problem cannot be solved even privately over the reals. Okay? This problem is really like something that, a simple problem that we can solve trivially without privacy restriction. When we want to do it using differential privacy, we must add some additional assumptions to the problem. For example, we must assume that the points are not arbitrary points on the reals. We must assume that there is some discretization of the real. So there is some finite domain in which the points, when I think about all possible data sets that I want to protect, there are only data sets of points on this segment, okay? It's not like arbitrary points on the reals. And this is really essential because there are results showing that if the points come from some finite grade x, grade x, then the end that we want, that we need in order to solve the interior point problem must grow in some way with this x. So in particular, it means that this x cannot be infinite. Okay, it must be finite. Yes.
If we have 4 points, then can't we just choose a point in the middle of the 2 interior ones, and then any upper points that you will change won't make any problem?
But even if you focus on the 2 middle ones, I can move one of the middle ones, like I did in the 2 points, and then the algorithm, your algorithm that just look at the 2 middle ones and output something there. If you look at the neighboring execution, when I change this point in the middle to the other side, will output something else, right?
Okay. So you needed to output exactly the same.
It's or at least like it should be. It must be a randomized. You must add some randomization because what we saw a differential private algorithm must be a randomized algorithm, and the output should be something which is like almost indistinguishable. Okay, and in your example, this algorithm is really distinguishable. One outputs something here, in the other it outputs something in a different segment. Okay. Okay, so let's look at let's give us some concrete solution to this problem. So let's assume that we have this grid, and let's see a simple upper bound of log the size of the grid. And we are even going to show this upper bound is not even for the interior point, it's even for this quasi-concave problem, general quasi-concave problem that we saw. We don't even need the quasi-concave assumption, we just need the sensitivity assumption. So basically, we have an algorithm, we have a function that has sensitivity 1. So basically what we do, we define a distribution over the domain, and for every for every y in the domain, we give it a score, which is proportional to this, which is basically the value of the function, and we sample like each element with probability that is proportional to this score. This is called this is one of the basic tools in differential physics. It's called the exponential mechanism. Okay. And basically, the intuition is that if points that have a high value, like the maximum, okay, will have higher probability to be chosen. Okay, so eventually we somehow define some kind of a distribution. We could output something maybe with smaller score, but the probabilities should be low. Okay, because elements with higher probability have with higher score have also higher probability to be chosen. Okay. So let's look at some kind of analysis for that. So the privacy analysis is basically immediate from this sensitivity assumption, because if we change the one point in the data set, then this function Q can change by at most 1. So all the probabilities of each element change by at most e to the epsilon factor, and therefore we get like immediate. It's called pure privacy. It's even with delta equals 0. It's a really pure, just an epsilon parameter. So this is the privacy analysis. And regarding utility, so basically, what is the analysis that we want to do? So let's denote like the maximum of the function by m, and let's think about this m like the Tukey depth, something that is proportional to the sample. Okay, like in the Tukey depth, the maximum was n over 2. So let's think about M as and M and N, the data set size as something like which is proportional to each other. So what is the probability that we fail? The probability that we fail is that we output something with score much smaller than 1 minus alpha, the maximum. Okay? So basically, we have at most X elements. Each such element with such small score, this is like the total probability mass of all those elements. This is what's in the what's written here. But we know that there is at least one element with the maximum. So the total number of scores is at least this factor. So eventually what we will get here, we will get x times this exponent, and which is small. You can do the calculation, which is small when the maximum is at least log x. And again, we think about m and n as something which is proportional to each other. Basically, it gives us basically says the following, that this algorithm will output something with the probability of failure will be low if the number of points is at least log the size of the domain. Okay? Again, we assume very strongly that the domain is finite. This algorithm doesn't work if x is like over the reals. There it's a real. So we really assume that we have only finite input spaces. Okay? Questions? Okay. So this is just to give you some concrete algorithm for this problem. And let's look what we know about this problem. So we basically defined three problems here. There is the quasi-concave optimization, and you can use it to do a private median, and you can also use it to do the private interior point. But actually, those two problems are not. There is a simple reduction. You can also from interior point you can do a private median. So those problems are somewhat equivalent. But basically, this is like the picture, and what do we know? So when delta equals 0, like this is like a pure privacy. Delta equals 0 is like the best privacy we can get. It's like we only have this epsilon problem. We don't have like a probability of something bad that could happen. So in this case, so we saw the upper bound of this log x, and there is also a lower bound of log x, and basically we pretty much know what's happening here. Okay, everything under pure privacy, the answer is simply log the size of the domain. Like the algorithm that we saw previously under pure privacy is tight. Okay, there is no better algorithm. What's happening in the approximate case when data is positive? So in this case, it turns out that we can do much better than the log x. If you think about this, x is a very large domain. It's finite, but it's still very, very large. We can actually do a private quasi-concave optimization with sample velocity 2 to the log star of x. Okay? Again, log star, it's how many logs we need to do in order to get to 1. Okay? And on the other hand, what's interesting is that for the interior point problem, we have median and interior problem. We have actually the result of the log star. So we know that log star is really the right answer for this specific interior point problem. And basically, so the point is that we have some kind of a gap, like those algorithms that achieve log star are tailored for this interior point problem and are not general as like this quasi-concave optimization. They really use like properties of this interior point problem, and the question is, can we somehow close this exponential gap between these two sample complexities? But it turns out that there is some kind of a lower bound. They're showing that this is, I don't know if we call it impossible, but there is some lower bound. I'm putting an asterisk here because the lower bound is not for every algorithm, it's only for algorithms that have some specific properties. But for such type of properties, we show that any algorithm must use at least 2 to the log star. Okay, so it seems that though this problem under approximate DP seems really harder than those simpler problems. There is really a separation between them. Okay, so why do we care about this quasi-concave optimization? Okay, because the interior point and private medians are something that we can understand. It's a natural problems. Why do we care about this quasi-concave optimization? So it turns out it's very useful for optimizing high-dimensional functions. And in particular, we will show that this is useful for doing a private center point in high dimension, basically estimating the median but in high dimension, and also for private linear programming, which in particular implies private pack learning of half spaces, one of the most fundamental learning tasks. Okay? And so we are going to show why this is useful for those problems, and so this is gives us some kind of motivation why we want to study this quasi-concave optimization. Okay, so now we talked about the Tukey depth in y dimension, and now we're going to extend it to high dimension, to dimension d. So the Tukey depth of a point, okay, basically the number of points that we need to remove such that x is not in the convex hull of the remaining points. Okay. For example, let's say that this is the set of points that we have. So basically there are a bunch of layers here. All the points, like from the blue to the green, I have Tukey depth 1. All the points from the green to the yellow have Tukey depth 2. From yellow to the red, Tukey depth 3, and so on. Okay? And some fact about this Tukey depth, so this is an extent. So like we knew that the median in the one dimension there is always a point with Tukey depth n over 2. In the high dimension there is always a point with n over d plus 1. Okay. Okay. So the goal, let's say that this is the goal. Now the data set are not points on the line, are points on RD, d-dimensional points. And our goal is somehow to output a point that is like a deep point somewhere inside, or even something in the convex hull of all the others, like an extension to the interior point problem. And so so what we do is like we only talked about like one-dimensional optimization. Now we have a d-dimensional problem. So I want to somehow convince us that I can use this one-dimensional tool to solve this d-dimensional problem. So the idea was done from Beimel from COLT 19. So let's find a good x coordinate after coordinate. What we're going to do, we're going to define, like for the first coordinate, a quasi-concave function. The function will be a function of qs of y. It's like we put y on this first coordinate and we take the others to the maximum. Okay, we want to find a point that has the maximal option to have a high Tukey depth. Okay, this is a one-dimensional function, and basically if we optimize it, we will find an x1 that has, like, because we know that the maximum is the size of s over b plus 1, we can find something close to it. And what's important is that to understand that this function is really quasi-concave, okay? Because otherwise we didn't do that because we have a quasi-concave optimization. But it turns out that this is really the case for this function that we define, because actually the 2kdef has a nice property. So if we take like 3 points on the same line, the value on the middle point will be always at least the minimum of the other two. Okay, and basically you can use this property to show that also those this one-dimensional function is also a quasi-concave, a one-dimensional quasi-concave function. Okay. Good. So what we do is after we we found x1 to xi minus 1 previously, now we define the ith function, which we put this y here, and we find the maximal continuation for the other coordinates. We optimize this function, and we lose a bit in the parameter, always an alpha error. But eventually we find like a good x1 to xd that has this high 2kdef, and now it's just playing with the parameters. We need to take this alpha to be small enough such that, let's say, something smaller than 1 over d, much smaller than 1 over d, and basically this is the algorithm. Okay, this is the algorithm. Just doing the quasi-concave optimization, coordinate by after coordinate. And it's important that those functions are different. They are quasi-concave, but they are not functions like the 2kdef that we saw in the y dimension. They are different functions. Okay, we cannot. It's not clear that you can solve those problems just by the one-dimensional interior point and the other. So this is why we really care about this quasi-concave thing. So let's see a different application, private linear programming. So let's say that now the S is a set of n linear constraints of the form of this form. So basically it's like d plus one dimensional points. So let's say those are like each half space is like a point in the data set. And now our goal is to find a point that satisfies all or most of the constraints, or most of the linear constraints. So basically, like here we also can define some kind of a depth function. The depth function will be the number of constraints that this point satisfies in this. Okay? And now this is a d-dimensional function. We want to optimize it, and maybe we can do it again, coordinate after coordinate. And just mentioning that there is a direct application of private pack learning. Just to see it, so basically in pack learning of half spaces, the data sets are points, and the goal is to find a half space that agree with most of the points. But if you look at a dual representation, you can replace points with half spaces, and the half space that you were looking at, you can replace it with a point. Like just by looking at the dual representation of points and half spaces, you can basically do a simple reduction between the two problems. Okay? Good. So for this problem, I'm just saying that this is not easy as in the 2kdef function, because this depth function is not quasi-concave like the 2kdef. Okay, because right here, let's say that this is one constraint is like this half space, and the other constraint is this one. So like we have disclosed the depth here as 1, the depth is 1, and here it's 2. Now I can really take like 3 points and where the value in the middle, the depth in the middle is smaller than the depth in the other two edges. But I'm not going to show, but basically there is a way to bypass this limitation. This is also from my paper from 2020. We can actually define some kind of a convexification of this function, basically finding a different function to optimize that it does satisfy this quasi-concave property, but also has some connection to the depth. Like if you find a point that says this C depth value, it translates to also high depth. So basically, we just optimize a different function and then deduce that also it has a good depth. Okay. But again, this C depth function, whatever this function is, also uses this quasi-concave optimization, the one-dimensional quasi-concave optimization as a building block. Okay, so this is the picture. Let's see what's it is. So we talked about those one-dimensional problems. We have some kind of separation, and we have those high-dimensional problems, which we know how to do with this private quasi-concave, one-dimensional private quasi-concave optimization, but basically gives us an upper bound of the form poly d times 2 to the log star. And now the question is, can we really, can we close this expression? Why, we can think of private interior point or private median, okay, as just let's say private center point is just a d-dimensional extension, high-dimensional extension of these problems, and so why do we need to really pay this 2 to the log star, okay? But on the other hand, this lower bound says that it seems that, if we cannot do private quasi-concave optimization, so maybe solving those problems will require a different approach, not go through this. And they actually, in their paper, they really interpret their result as saying that in order to solve those problems, we need to find probably a different approach for this high-dimensional tasks.
So just to make sure, if in the version where you try to get the private center in high dimension through iteratively optimize, so if you could have translated each step to a private interior point in one dimension, then you would have an upper bound that would look something like poly d times log star instead of 2 to the log star. But because right now each iteration is solved as a general quasi-concave optimization problem, then you get the 2 to the...
Exactly. But basically now we're going to get to our result. So our result is basically bypassing this limitation. So, yes.
Just to understand the upper bound and the lower bound, what exactly is log star and the O with the line above it?
There is also I think dependence log star dependencies. Yeah, it's logarithmic in log star dependencies here somewhere, given that. Yeah. So.
What are log star dependencies?
No, the main dependency in the main side is 2 to the log star. Okay.
What is log star?
What is log star?
Yeah, exactly.
Okay, log star is the number log star of n or something is the number of logs that we need to apply in order to reach to 1. Okay. Usually it's very small now. Okay, it's log star in any reason will say it's something which can be seen as a constant, but still theoretically we are doing a theory here. We think about it as still not a constant. Okay, it's still a function that goes with the size. Okay, and as long as maybe in any practical interpretation there is no difference between 2 to the log star and log star, theoretically there is. Okay, it's still some kind of an exponential gap. Okay, I think that Mark Beimel mentioned is the smallest exponential gap that there, but it's still an exponential gap. Yeah, and I think it's more like those algorithms we are talking about. Kind of those algorithms are. It's a very fundamental problem. It's like the interior point. I think it's a very fundamental problem, and trying to understand the sample complexity of very fundamental problems. It's something which we should be able to do. Okay, and if we have such gaps between such exponential gaps, it seems something that we would like to avoid, even if they don't have like what. So those are all those algorithms that the log star just mentioned. They are not inefficient. So we're not talking about they are inefficient in the running time. Okay, and I will later talk about some efficient, maybe efficient algorithms, but they are inefficient. The one-dimensional problems are efficient. Efficient in polynomial in log of x. But those high-dimensional problems, because of the quasi-concave functions are very complicated, they are inefficient. Those algorithms, just to optimize those complex functions.
So log star is log of
Yeah.
number of times as the parameter inside.
Yeah. Okay. Yeah. Okay. So in our work, what we showed a weaker task. We are not aiming for private quasi-concave optimization of any quasi-concave function. We are only aiming to optimize quasi-concave functions that are also have some kind of approximation property. And then we showed like two things. On the one hand, we showed that just for aiming for such functions, we can really do that using the interior point. There is a reduction. Okay? And then we gain this log star instead of this 2 to the log star. But also, this is enough for all those geometric problems that we saw. Okay, we don't have to go to this complex mechanism here. We can also use only this one that uses the interior point and gain this improved sample complexity. Okay. Okay. So now let's see what is this approximate function. So okay. So I think what's your name? Yuval. Okay, you talked about it first, so I will just try to explain it again. So a function, we said that the function is approximated if you take a random sample, basically the relative value is almost the same. Like if you see an example, let's say that we are thinking about the Tukey def. I'm going to show the Tukey def is actually an approximate function. So we have a bunch of points on the line. Let's look at this point here. And now let's take a subset of size 10. So the relative depth of those 2 points is almost the same. This is half and this is almost half.
What is the quantifier on S? The probability is also oversampling S from something, or this
The
is
probability over a random subset.
So it's the function of S. So when you say Q is blah blah blah, it means for any S. So Q is a function for any subset of size n. But that might still depend on the full data set.
Yeah, so it doesn't matter what is the full data.
So
the full data set is larger than n, and you want to say that it doesn't matter, like, as long as it has subsets of size n, and you take a random one, then you will get this property.
So if this property depends on S, so that will be the worst case overall big data set.
But it doesn't matter. Yeah, it's independent. Like it doesn't matter what is this S. Like here, it doesn't matter which points you will take on the line. Enough points that you take on the line, if you take a random sample, you will get like preserve the relative depth of any point on the line.
So we can have it for all S.
Yes.
Like this.
As for all S. Exactly. For all S. Okay. Seems like strong requirement, but it turns out that this stronger really what we have in the problems that we describe in the d-dimensional problems. And So it turns out that the Tukey depth and also this the function are actually approximated functions to this y. Basically, if you take like number of points, which is d over alpha square, something like that, you will get some alpha approximation. Why is that? This is some direct application of VC dimension. So the VC dimension of half spaces is d plus 1. So basically, you can use like VC statement to show that it's really happens. Okay, it's this is basically you can replace it. This is like the VC dimension here, the d here, and the same alpha square of the errors of VC theorems. Okay. And okay, so good. So assume that we have this. So we know that we want to optimize nice functions. So how can we do this reduction to? Now we have the one-dimensional quasi-concave optimization of just approximated functions. How can we do it using the interior point? How this approximation helps us to do the optimization. So the idea, take the data set and use a random partition into m-size subsets, okay? Now we have m-size subsets, each is like a random subset. We compute in each subset the maximal solution, like non-privately. We just compute non-privately what is the maximal solution. And then we just put it in the private interior point box and just get the y. Okay, this is the algorithm. What's the analysis? What's the utility? So the privacy is simply, if we change one point here, then only one of those elements, like let's say 1 point here only belongs to one of the data sets, which affects only one of the points. And because only one of the points changed by changing 1 point here, then private interior point just protect us from this. We get the privacy just by the privacy guarantee of the interior point algorithm. So what is the utility analysis?
This is kind of a reduction from the private interior point to the difficult.
Yes, yes, exactly. So the utility analysis is the following. So because the function is approximated, we know that all those x1, x2 to xt has high value with respect to the random data set. But because the function is approximated, we know that they also have high value with respect to the original data set. Okay, this is exactly the approximation guarantee. So we know that all those values with respect to S, not those S1 to S, also with respect to S, are also high, also close to the maximum. And now we have an interior point y of those x1 to xt, and because y is interior point of points that all have like a high value, then just by the quasi-concave property of the function, we get that this y also has a high value. Okay? And that's it. The algorithm is simple. There is nothing more than that. There is a cost to this, what we are doing here. The dependency of, because the dependency of the dimension that we use here is a bit larger than, it's not a bit larger, it's larger than it's still polynomial, but larger than the previous work, what they did. Like they had like d to the 2.5, and we have here like d to the 5.5, and it's still open, I will show you in the next slides, but just for the question of can we get log star sample complexity that depends also polynomial in D, this is the algorithm. Okay? And the answer is yes, we can. We are not, basically the lower bound of the quasi-concave that we have the 2 to the log star doesn't really say anything about those problems. Okay? Okay. How much time? Well,
About 5 minutes.
okay, so let's go to the summary. So we present this private quasi-concave optimization, bypass this lower bound. I just want to mention that it's not clear that we bypass only the lower bound because we use the approximation, because the lower bound is also, it's not a lower bound for any algorithm. It's a strange lower bound. Okay, the lower bound usually say that if you have algorithm with some specific property, then you must use 2 to the log star. So it could be possible that there is a different algorithm for this task that doesn't need to assume this approximation that somehow can solve the problem with log star. We don't know. It's still open. Okay. And we give this first poly the log star x and sample complexity. And regarding the open problems. So again, as I said, reduce the dependency in D while avoiding the exponential blow up in log x, log star of x. Okay, something that is still open. And I think that like maybe, you know, if you think about a more important question, at least in my opinion, can we achieve the log star or even the 2 to the log star algorithms in polynomial time? Because all those algorithms are inefficient. They use something like n to the d running time. And actually there is a result from the last STOC showing that you can solve the problem in polynomial time, but the sample complexity is like polylog of x and not log star. Okay? So if you don't care about paying sample complexity logarithmic in x or polylogarithmic in x, we have a polynomial time algorithm, but it's still, we don't know like how to achieve it, you know, to get like gain both the small sample complexity and efficient algorithm. So this is still open. And I think that this is more important than, I don't know. No, this is, what problems are important, but in my opinion, this is really a challenging thing to understand. And I think that that's it. Thank you.
Can you go back to the definition of the function, what do you call it? Here.
Yeah.
Function approximated indefinitely. Oh, I see that any subset of, okay, no, I missed it. It's a subset relative to the full function. That for any 2 subsets, the value.
No, yes, subsets for the,
Okay.
yes.
That's kind of a more general question about the research in this field. Usually what you try to do is to kind of create a new assumption or maybe kind of like an approximated function to get better results, or are there like, how
So-
does it usually do?
So there are results, for example, you have efficient algorithm, better algorithms from maybe, let's say, linear and half spaces and things like that, but they assume, let's say, a large margin assumptions or things like that. So if you add there are some additional assumptions that you can add to the problem that make it much easier. Okay, but like those type of problems are trying to avoid this large margin assumption. They do assume that this discretization of the world, okay, that we are not talking about like RD, we are talking about some domain of the RD, some finite domain, but still, you know, trying to understand this minimal sample complexity with respect to this very natural assumption. Yeah, but you can add other assumptions as well that can change the, can make the problem easy.
So you actually try to cut off assumptions.
Yes, yes. In this type of thing, this is like with the minimal assumptions that we're there. Eventually we solve here like we'll provide pack learning answer with like the minimal assumption that you can like. We cannot do it with infinite domain, so this is like the minimal assumption we can hope for.
No one else has. Is this a definition you came up with? Is it known in other places?
We didn't took it like from what I said before, like the approach of like taking a subset and and split it into random subsets and doing some analysis, like aggregate the non-private result. This is like a very common approach in privacy. It's called subsample and aggregate. This appears in many papers. This specific property, I won't be surprised appear in other settings, but we didn't like took it from some paper and it's basically what we did here for the analysis to.
It sounds like some kind of a statistical property of estimator or something that should have been well studied somewhere, but I've never heard of it. And
I
it
guess
seems
that
very useful.
as I said, proving that the Tukey depth and all those are approximated, it appears in paper from very old papers. You can see yours very open, but it still doesn't mean that they didn't study it in the privacy context.
Yeah.
So taking those basically, like I'm saying that those functions that we care about are approximated because we use like old theorems from 40 years ago. It's but eventually, the context is like trying to understand that this is basically what we wanted. I don't know if maybe someone used some kind of a property for like a different setting, not for this quantitative optimization.
Thank you then.